Hello everyone, Assalamu alaikum. So for P2 last time we were doing the last topics past paper questions, and I told you that these past paper questions are not basically from P2 of last year's, rather I have extracted all these questions from P4, means for A2 level, from the past 10 to 12 years questions. So I have extracted as much as required for P2, as in we studied last time that we have seen it in the syllabus that only the conceptual questions will come, and you won't be requiring any code to be written or write for UDTs. So let us start. Let us continue from the point where we have left. So we solved question until October November 2012 P32, and now we'll start from October November 2012 P33. All right. Now my microphone is fine, but microphone is fine. Everyone, can you hear me? All right. Okay. Let me check on your side. We are fine here. Others say yes. All right. So this is October, November 12 P33. Describe an operation. Describe the operation of a linear queue data structure. Linear queue data structure, and that is first in, first out. That is what the operation is. First in, first out. Or you can write like whatever the first item to join this structure will be the first item to leave. First item to join the data structure queue will be the first to leave. All right, that is first in, first out. A linear queue is to be implemented to store data using the following variable: my queue, an array of 100 elements of a string data type, head of the queue from where we have to start, and tail of the queue. All right, from head of the queue we actually delete, and from the tail we actually add, and then the new item. Now it says that the diagram shows the state of my queue, head of queue, and tail of queue. Remember, from the head we delete, head as in front and tail as in rear. So we always add at the tail. The diagram shows the state of my queue, head of queue, and tail of queue after four variables: owl, loin, giraffe, and camel have been inserted, and one value owl has been deleted. All right. So these both pointers are moving forward. When you are actually adding, tail Q is moving forward, and when you are deleting, head Q is moving forward. So head Q is now pointing to loin. So the next item that will be deleted from the queue will be loin. And since owl is deleted, head Q is already moved, has already moved forward. Inserting and deleting single item to and from the queue are to be implemented with two procedures: add to queue and remove from the queue respectively. Shown below is the incomplete pseudocode for add to queue procedure. So add to queue first looks for if the tail of the queue is at 101. Hold on, please. All right. So if we have to check if tail of Q has gone out of the range, means if it is 101, then output refuse Q is already full. Else input new item and tail of Q, input new item, tail of Q is equal to tail of Q plus 1. Achha, we have to add that item. I think that space is actually removed. So we have to write now my Q tail of Q is equal to new item, and tail of Q is equal to tail of Q plus 1. All right, so this is a simple, that is why I have kept it. Otherwise in syllabus they say that you won't have to write any pseudocode for it, but still there are chances that still you are not writing pseudocode, but there might be a simple written fill in the blanks holding question that you might need to fill. So that is why I am actually holding such questions. Write the algorithm for the remove from the queue procedure using the variables given. So remove from the queue will be rather easy. All we have to do is to check if head of the queue, what was it? Head of the queue, yes. So first we have to check if I'm writing under procedure remove from the queue. If head of the queue is actually tail of the queue. If they both are same, then you see they both are moving forward. Both pointers are moving forward. So one is adding, the other one is removing. All right. So let's have a look back at it. They say that owl is already removed and the second one will be loin. Okay, in that case, head should be tail plus one, because whatever that is removed, head has moved past to it. So it means that when this last one, camel, will be removed, head would be then at 4. So we have to check that if head of the queue is equal to tail of the queue plus 1, then output underflow queue is empty. Else output my queue head of the pointer, head of the queue, and then we have to move head of queue is equal to head of queue plus 1. And if that's it. And then we would have end procedure. There's a question. Let's take this question. Sir, why tail of q plus 1? I just told you in the question what they say. They say, and one value owl, and one value owl has been deleted. So if the owl is deleted, head of q is at what loin? When this camel will be deleted, the last item, head of q will be here. You see over here, loin is not yet deleted. So when it moves forward, how we would know that it has deleted the last item? Last item would be the one where the tail of the queue is pointing to. So when this last item will be deleted, as we have observed over here, that since owl is deleted, not the loin, and head of the queue is pointing to line. So when this camel will be deleted, the head of the queue will be pointing to tail of the queue plus 1, which is 4. Get the idea, Ram? All right. Now, next question. A linked list is implemented with an array. A linked list is implemented with an array. All right, there is a C part as well. The C part says, describe an application in the operations of computer system where the queue data structure would be required. Printing. Printing queue. In printing queue. In printing queue, the job that goes first will get out first. So there is a question. Sir, आपको I'm sorry. All right. A linked list is implemented with an array of records of data node, data type node. The node record has two fields as defined below, the data and the pointer. So we have a linked list and it has got nodes that has data and node pointer. So we would have something like this, and when the list ends we would have one null pointer. So this is our head pointer. It is pointing to the first node. Every single of this structure is called node, and this node is made against this record. All right, so now a program is to create a linked list using the array and variable shown below. Identifier is mylist, which is an array of 100 node elements, and head pointer, which is basically pointing to the first node. Explain the difference between static and dynamic data structure. We have actually covered it in last lecture, so I'm not going to discuss it anymore. What benefit would be gained from using dynamic data structure to implement a linked list? So basically, dynamic data structure matches the size of the data requirement. If we need some more data, we actually take that data and then we collect some more space from the memory and we put the data in that memory. Similarly, when we don't need the data, we release the data as well as that node so that other programs can utilize it. So dynamic data structure matches the data requirement. Takes memory when it is required, as much as that is required. I told you that the amount of the memory that is taken by the linked list on the go from the memory is called what? Heap. All right, so there is no wasted memory space. That is why it is always beneficial to have dynamic data structure. The linked list has the following items: bean, cogged, apple, pepper. The data is to store as follow. Okay, so head pointer is basically pointing to 3, which is apple. Apple is pointing to 1, which is bean. Bean is pointing to 2. 2 is pointing to 4, and 4 is pointing to null pointer. What is the value? What is the value of my list head pointer dot data? So head pointer is 3. This is my list. My list head pointer dot data is basically apple, and my list head pointer dot pointer is basically 1. All right, complete the linked list diagram by filling in the data and pointer values for each node. Now you can see that in this particular my list, items are haphazard and they are being sequenced using only the pointer. So when we draw this in this hypothetical diagram, we will write all the items in the sequence. All right. So head pointer is pointing to 3. 3 is apple. Apple is pointing to 1. 1 is basically bean. It's pointing to 2. This is pointing to 4. And this is then pointing to null pointer. You get 4 marks by having 1 mark here, 1 mark at the null pointer, 1 mark for all the pointers, and 1 mark for all the values if they are put properly. Okay. Now, October, November 2013, P31. It says, describe the operation of stack data structure. And stack data structure's operation is last in, first out, as in the item added in the end will be the first to be removed, or item added at the first will leave at the end. So a stack is to be implemented to manage the spooled print job sent to a network printer. A job reference and the user ID of the network account are recorded for each print job. The stack is implemented using the following user-defined type and variables. All right. All right. So type is stack. It has got job reference number and user ID. So this is a spool job, which is an array of type stack. So this is a spool job. It has got top of stack pointer here, new reference number, that will be the value that will be the variable that we will use to input the data, and user ID. So they want us to actually understand this part. So the diagram shows the state of spool job and top of a stack after 3 print jobs were received from the user Lavis, Chi, and Singh in that order. So Lavis, Chi, and Singh. A print job was sent to the printer, then a new print job received from the user Harris. So this job from the Singh has been sent to the printer. It is being printed, and there is another job from the Harris, and obviously this is basically last in first out operation. So the Singh's job will be printed first, although the Lavis was the first person who sent the job. But since it says that last in first out, all right, so the job of Singh will be printed. So when the job related to Lavis will be printed, only when all of the jobs above it. So it is kind of disadvantage when we are using stack for printing, that the one who would send the job first will have the job printed at the end. So Instead of using stack, it is a good idea to use queue, which says first in, first out. Let's say spool job 2 dot user id spool job 2 dot user id is 17856 Harris 17856, and spool job top of stack -1. Top of stack -1 is this job dot job reference. Sorry, they have asked for user ID. User ID is Harris. Spool job top of stack is 2 -1 1. So spool job 1 minus job reference will be 17843. Okay. Spooling a new print job is to be implemented with procedure push job. Shown below is the incomplete pseudocode for the push job. Using the variable and user-defined type given, fill in the missing pseudocode. Procedure push job. All right. If top of stack is equal to 100, then output stack is already full. As we can see over here, top of stack is pointing to the item which was added at the end. All right, top of stack is pointing to the item which was added at the end. So when we will add all 100 items, top of stack will be pointing to 100. So if it is already, is it 100 or 1000? Sorry, 1000. So if it is already at 1000, it means that we don't have any more spaces available. So then output stack is already full. Else input user ID, and then we have to input second thing, which was input reference, job reference, input new reference number. Input new reference number, and then top of stack is equal to top of stack plus 1. We have to move it first. Spool job top of stack dot reference number is equal to new reference number, and similarly spool job top of stack dot user ID is equal to new user ID. That is very simple. So we have to check for error, and if there is no error, then we move the data in. Now, processing a print job is to be implemented with pop job procedure. Complete the pseudocode for this pop job procedure. So if top of stack is equal to -1, so that is basically when there is no job in the stack, then output there are no print jobs. There are no print jobs anymore. Else process spool job, which is basically top of a stack, and then we will move top of a stack -1. All right. Explain why the choice of stack data structure for this application is a poor choice. Obviously, I told you this is not fair that the one who has sent the job first, their job will be printed at the end because of the nature of the data structure, which is stack. So it is a good idea to use what? Suggest an alternative data structure. So this is a good idea to use queue. So the answer would be, it is not fair to put the user who has sent the job at first at the end. So some jobs may wait a long time before printing because they were sent at the start. Better choice is Q. Since print job sent will be the first to be out, so it has to be first in, first out, which is basically the nature of Q. Now, October, November 13 P32. A customer names are stored in array custom. An algorithm is to be designed to perform a serial search of the array for a requested customer name. The algorithm will use the variable shown in the table. Study the table and algorithm and fill in the gaps. So customer is an array of 100 elements of a string. Index is an integer. Is found is basically, as the name suggests, is Boolean. And we will use it as a flag to be updated when we are looking for names in the array. So a flag used for searching algorithms. So serial search algorithm. So we know how to do that. This is not basically related to UDT, so I am going to skip it. Describe the operation of stack. Describe the operation of stack. October, November 2014 P32. Last in, first out. Last item added is the first to leave the structure. All right. Now, an expression in reverse polish notation can be evaluated on the computer. Reverse polish notation is part of P3, so leave it. Give one further use of stack data structure by the computer. So for functions and procedures, subroutine calling. What is subroutine calling control? There is a question afterwards. We will solve that question, then you would have an idea. Part B is left for a previous question. Part B of the previous question. How many comparisons on average will be needed to find a requested customer from the customer array? This is average. They have asked for what? Average. Okay, so part B will be actually how many items are there? 100. All right. So the average will be 50. Okay, half of the number of customers. So now describe the operation of stack. We have discussed it. I told you that reverse polish notation is part of P3, so I'm not going to assert on it. Move on. Give one further use of stack data structure by computer system. So I said that subroutine calling control. And what is subroutine calling control? We will discuss it shortly because there is one more question which will only be asking from this reference. Describe the operation of the queue that is first in, first out, which that means that the item that enters the data structure will leave the data structure first. All right. There is one more thing coming to my mind for the use of stack data structure. You see, we use undo, Control Z. So the action that we have performed at the end will be undone first. So controlling undo operations in word process. Whatever the thing that you would have done at the end will be basically the first to be undone. Sir, in the new 9618 syllabus, they have mentioned that pseudocode of ADTs will not be asked. That is correct. Pseudocodes of ADT will not be asked. That is correct, but that is as a whole. So I suspect that they might give fill in the blanks based pseudocodes for two of the data structures that we are studying, stack and queue, as they are very simple. All right, so there might be fill in the blanks pseudocodes, not as a whole. They won't be asking you to write the whole pseudocode, but they might ask you to fill in the blanks from your conceptual perspective. Controlling undo operations. Okay. Now, a stack A and QB are to be implemented as follows. Stack and queues. Stack A has a single pointer top of stack TOS, which shows the index position available for the next new item to be added, which is to be pushed to the stack. QB is controlled by two pointers, head and tail. The diagram shows stack A and QB after two items have been added to each. All right. So it means that the next item that will be deleted would be this one, string 3. And the next item that will be added to stack will be at position 3. So you have to actually first make your mind up. So top of stack is pointing to the position where the next item will be added. It means that you will add where the top of stack is, and then you will increase the top of the stack. Sometimes these depictions, these diagrams show the top of a stack is not at the empty location, rather it is at the location where the last string was added. In that case, you will increase the top of stack first and then you will add it. But in this case, you will add first and then you will move the top of the stack. Similarly, over here, head pointer is pointing to the location, which is 1 to string 3, which will be removed next. It has not yet been removed. So we will remove and then we move the head pointer. On contrary, for the tail pointer, we will move the tail pointer first and then we will add it, because tail pointer is pointing to the last added location. So it has to move forward first and then we will add to it. So head is deleting from the position where it is pointing to. Tail is basically pointing to the position where it has added the last item. So it will be moving first and adding later. So you have to actually pick up whether to move first and then add, or to add first and then move forward. So this is basically the nature that you have to actually understand first from the given depictions. So stack and QB are both initially empty. The sequence of 6 items of a string goat, cat, sheep, chimp, cow, horse is stored in stack. All right. Show on the diagram below the contents of a stack A and its pointer at this stage 1. So you are seeing that the pointer is pointing to the location which is the next available location. So let's add first goat, cat, sheep, chimp, goat, cat, sheep, chimpanzee, and the last one is then cow and horse. Then cow and horse. And then your top of a stack pointer is pointing to 7, where the next item will be added, as the case over here. All right, now The content of stack A are then removed and placed on queue B. The content of stack A are then removed and placed on queue B. So the nature of a stack is last in, first out. So show on the diagram below the content of queue B and its pointer at this stage 2. So horse will be removed first and placed over the queue. Horse. Then cow. Then chimpanzee. Then sheep. Then cat. And then goat. You see, the nature is first in, first out, and over here last in, first out. So last in was horse. So horse will be added to the queue first, and then cow, then chimpanzee, then sheep, then cat, then goat. And the pointer, let's make the pointer. So the first pointer will be pointing to the first item head, where it will be deleted, head. And second pointer tail will be pointing to the pointer to the location where the last item was added. So items are being added from the tail and are being removed from the head. And remember, the horse is not yet deleted. All right. Now, show on the diagram below the content of QB. Three items are removed from QB. Three items are removed from QB and input on stack A. So this is first in, first out. So horse will be deleted first and will be added to stack A. Then cow, and then chimpanzee. And top of a stack will be pointing to this location. Show on the diagram below the content of stack A and its pointer at this stage 3. So this is done. Three more items are removed. Three more items are removed from the QB and placed on stack A. Means first we moved from stack A to QB. Stack A got emptied, and then from QB to stack A reverse. But if you have noticed, the item that was added at the end in the stack, when after being through the queue, it was added, it is the first item of the stack now. So the whole thing is inversed. So three more items are removed from QB and placed on stack. Comment on the final content of stack A. Stack A has all items inversed, reversed. All right. Items, or you may write in reversed order, whatever. Okay, so if there is a stack, you are adding item to it, items will be added in the last in, first out manner. When you remove, the item that was added at the end will be removed first, and if you are adding it to the queue, that will become the first item in the queue. Afterwards, if you move from the queue back to the stack, every item in the stack will be inversed. Okay. So May, June 2015, P3132. Briefly describe the operation of a stack data structure, last in, first out. High school language programs make extensive use of subroutines. Now you have to remember that thing which I told you about, that we use a stack in controlling the subroutine calling system. Subroutine calling system. So this is with that particular perspective. High-level language programs make extensive use of subroutines. A stack is used to store the data about each subroutine call. The data are the return addresses, the register content, and the value of all local variables. When one subroutine calls another subroutine, from which line it was called and at which line, obviously the subsequent one, where this control will come back, will be added to the stack, and whatever the register contents of the microprocessor at that moment, when one program is switching to another, one subroutine is switching to another, will also be added to the stack. And then the values of all the local variables will also be added to the stack. So these three things, when one subroutine calls to another subroutine, are basically added to the stack. So that when the system comes back after covering up the called subroutine, all the local variables values, the register content, and from the line where the system left could continue. Okay. A student project is to simulate the saving and retrieval of the data for subroutine calls. The student simplifies this for their project and will store on the stack only the return address. Only the return address. Now, basically, what is happening? There is a stack over here which is empty, and top of a stack is pointing in here. The main program starts. There are statements, and then it calls subroutine sub1. So when it gets back, it should not come back at this particular line, rather it should come back over here, because this line when executed is calling the subroutine. So this 173 will be added to the stack, so that when system comes back, system would have an idea where to start from. Then from here, system jumps to procedure sub1, and then from procedure sub1 starts execution, and at this particular point it calls subroutine 2. But before going to subroutine 2, in stack it will actually insert 269, so that when it comes back it could continue from 269. So from here 268 it goes to subroutine 2, which is at address 321. So from here it starts executing the program and it ends. When it ends, system pops from the stack, which is 269, and gets back at 269 over here. From 269 it starts execution, and at 280 it calls subroutine 3. But before calling to subroutine 3, it pushes 281 to the stack, so that it has an idea that when it gets back, it will get back at 281. So it calls subroutine 3. Subroutine 3 is at address 400. When it starts execution, it ends. When it ends, it goes back to 281 and starts execution. When it goes to 281, 281 is popped. So now we have got 173. From 281, it ends the procedure. When it ends the procedure, it means that this 173 will be taken out again, and the pointer will then point to the bottom, and system from here goes back to 173. And from 173, it will end the program. So you see, you have to actually, so these addresses are saved in different stacks. No, this is the same stack. I'm just making one after the other so that you have an idea that it was empty first, then one procedure call, then another procedure call, then systems come back, then another procedure call, then systems comes back, and then comes back to the main. So basically what happened, you have to actually pay attention. So main program called over here subroutine 1. Subroutine 1 then called subroutine 2. Subroutine 2 then ended and systems comes back to subroutine 1. Subroutine 1 then calls subroutine 3. Subroutine 3 when ended, it gets back to subroutine 1. And then subroutine 1 finishes and then it gets back to the main program. So this order of calling is being controlled using this stack. Order of calling subroutines must be in order of calls made. Let's say A goes B, B goes C, C goes D, D goes B. So it does not mean when B finishes again, B comes back to D, D goes back to C, C goes back to B, and then B goes back to A. So if one of the subroutine is being called again, it is being called as a new one, not the one that got frozen when it had called another subroutine. So the beauty of subroutine is that they are actually parts of the program which can be called multiple times. Every time if they are called, not in a way that system is getting back from where they have called, rather they are being called from the subroutine like they are never called back, they are never called before it. So they will be used as separate subroutine. So one subroutine can be called hundreds of the times, and every time it is called, it will be called in a way that it is called freshly. So these addresses are saved in different stacks, no, in the same stack. So you see, they have asked you to do this. Okay, so 173, and then you would have 173 and 269, and then afterwards you have got 173 again, and then 173, 281, and then 173, and then it becomes empty. All right, that is how it works. Complete the diagram to show the contents that we have done it. Okay, now if top of stack is equal to 100, then output stack full. No more data entry. All right. Else input new addresses. New addresses, how? They have given us this variable new address. Input new address. Top of stack is equal to top of stack plus 1. And then stack at top of stack is equal to new address. The student uses the procedure pop address to simulate retrieving a return address from the stack. Complete the pseudocode for this pop address procedure. So what do we have to actually check? If top of a stack is equal to 0, if top of a stack is equal to 0 or top of a stack is equal to less than 1, then output there are no current procedure calls. Otherwise output address, and then we will actually output it, and then we have to reduce top of a stack. Top of a stack is equal to top of a stack minus 1. All right. Now, May, June 2015, P33. So this is same sort of question, so I'm going to skip it. Let's get to this question now. May, June 2015, P43. A stack abstract data type has these associated operations: create stack, add items push, and remove items pop. So we have created a stack. Okay, so a stack is created. Okay, so now the stack ADT is to be implemented as a linked list. A stack ADT as linked list. So basically, a stack is implemented using linked list, and linked list is being implemented using array. So this question is covering this part. A stack is being implemented using linked list. Each node consists of data and pointers to the next node. There is one pointer, the top of a stack pointer, which points to the last item added to the stack, which points to the last item that is added to the stack. There is one pointer, the top of a stack pointer, which points to the last item added to the stack. Draw a diagram to show the final state of the stack after the following operations are carried out. So create a stack, we have created this stack. Pointer is pointing to nothing because there is nothing in here. Then you have added Ali. Then you have added ZAK. Then you pop. When you pop, you are left with Ali only. Then you push Ben, okay. Then you push Ahmad, okay. Now your pointer is pointing to Ahmad. Then you pop. When you pop, you are left with Ali and Ben. Now system is pointing to Ben. And then you pop Jatinder. So in this case, you have Ali, Ben, and Jatinder. And pointer is pointing to this position. Now basically what is happening, Ali is at the bottom, Ben is on top of it, Jatinder is on top of that. Top of stack pointer is pointing to Jatinder. Jatinder is then actually pointing to Ben, and Ben is then pointing to Ali, and Ali is the last item in the stack. All right, Ali is the last item in the stack. So that is what they are expecting you to know, that how to implement stack through linked list. Okay, so these items are no more used. Top of a stack is there. If there will be another item that will be added on top of Jatinder, and that will be pointing to this. All right, so you have to take the operation of linked list in your mind, and then you will be actually implementing it over here. All right, so stack is something like this. Now, using pseudocode, a record type node is declared as follows. Declare array 1 of 10 of nodes. So this is the array 1 of 10 of nodes. Reserves space for 10 nodes in array stack. The create stack operation links all the nodes and initializes the top of the stack pointer and free pointer. Complete the diagram. Top of the stack pointer would be 0. Top of the stack pointer will be 0. Why it is 0? Because it is not pointing to any location. And I told you that when there is no item in the linked list, it means that the whole arrangement is basically the free list. So free list will be pointing to 1, 1 will be pointing to 2, 2 to 3, 3 to 4, 4 to 5, 5 to 6, 6 to 7, 7 to 8, 8 to 9, 9 to 10, and 10 will be pointing to 0. So this is basically a new list, which is a free list because there is no item yet added to it. All right, so when the new item will be added, it will be added where the free list is pointing to, if you do remember from my lecture. And then top of the stack will become 1 and free list will be pointing to 2. So this is one idea. So this is it. All the questions are actually solved. So UDTs are being introduced for the very first time. So you have to actually listen to all 3 lectures that we have completed. First, where I actually introduced all 3 UDTs, stack, queues, and linked list. And second, where I started off with these selected questions from past papers of P4 and P3. And then today the third lecture where we have completed it. Every single question I have carefully chosen to cover all of the aspects, the concepts of these 3 UDTs. So I hope that I would have made these UDTs simpler for you, and it is all there. And whenever you like, you can review these. If there are any questions, please do ask those questions in your respective groups. Anything now? Arham, Manahil, Abdullah, Muskan, Umar,